Now I'm going to finish the first version of the cat program. That's going to involve designing two functions. So in that way, it's going to be quite familiar. We'll go through the HTDF recipe twice. But we're going to be designing those functions in the context of a partially complete larger program. That's something that gets to be more and more important as we go forward. As the programs get bigger, we often have lots of incomplete functions that we need to finish before we're done. And the most important thing in this video is going to be how to use the wish list mechanism to keep track of that work that remains to be done. We have a constants part of the file, which we know corresponds to the constants part of the analysis. We have a data definitions part of the file that includes a world state type, cat, which we know corresponds to the changing information part of the analysis. We have a main function that calls Big Bang with two options, on tick and to draw. And now if we've forgotten exactly what we have to do, I'll just search for 3 exclamation marks, and very quickly I see exactly what I have to do. And if this program was larger, I could go here and say show program contour, and I'd see off to the right a picture of the whole program, and you can barely see it there, but the places where the search has found 3 exclamation marks are highlighted. So if I had a very big program, I could go over here and quickly jump to those places like that. I'll hide that for now because we don't have that big a program. So now what do I have to do? Well, this tells me, hey, you're partway through an HTDF problem. Here's the problem. You've got a function that consumes a cat and produces a cat. This is an HTDF problem consuming cat. It consumes cat, produces the next cat by advancing it 1 pixel to the right. If I'm a little bit unsure about what a cat is, I can scroll up here to the data definitions and see, oh, a cat is number, and here's some good examples. And it's interpreted as the x position of the cat in screen coordinates. Okay, well, signature purpose stub, the next step is examples. Let's see, what's a good first example? We'll say check, expect, advance cat of, I don't know, 3. And we advance it by 1 pixel to the right, so that should produce 4. And let's see, this function is it behaves consistently independent of the number we get it, so I really should only need 1 test. I'll run the test to make sure that they're well formed. The test is running but failing, so it's well formed. This was the stub. I'll comment it out. I'll say use template from cat. I'll go up here and get the template. I'll copy it. I'll just label this as being the stub. I rename this to advance cat. And let's see, I've got to fill in the dots. I advance it 1 pixel to the right. Oh, this is just plus C1. Or if you want, there happens to be a function called add1. We could just use that, but I'll just say plus C1. Now I'll run again. My test passed. So let's see, I've done that piece of the wish list. I go back again looking for 3 exclamation marks. Here's another function. It consumes cat and produces image. And it's supposed to render the cat image at an appropriate place on MTS. And now I say to myself, well, what's the cat image? I'll look up in the constants. Oh yeah, there's a thing called cat image. And I'll say to myself, well, what's the appropriate place? I'll go look at the cat data definition. Cat is number, so cat itself is a number, and I interpret that as the x position. So I've got the x position, and I remember now that the y position doesn't change, so I'll look in the constants for it too. There it is, center y. So now I've got a pretty good idea about how this is going to work. Signature purpose stub, the next thing is examples. So check, expect, render of some cat, let's say 4. What's that supposed to produce? So render 4 does what? Well, there is this primitive called placeImage. And what we need to do is we need to take the image of the cat, which is cat image. We need to put it at a certain xy location, which is 4 and center dash y. And the background that we're going to put it on is MTS. Now I wrote that quickly because I remember exactly how placeImage works. If it takes you longer to write the expected result for a render function, don't worry about that at all. You're figuring out how the image functions work, what you're going to use in order to produce the image you want. Time spent here on this example translates into time saved when you do the actual function. So let me run this. And we have a failing test, which is what we'd expect. One thing that's nice to do with these render functions is actually look at the failing tests. Let's see, we're getting an empty scene because the stub always produces the empty scene. But what's useful to do, let me just make this bigger, is to look at the expected result and see if our test makes sense. And that seems about right. We've got a cat there that's nose is a little bit off the edge. Remember, placeImage places the center of cat image, in other words, kind of the center of this cat, at the specified position. So it's putting the center of the cat at 4 and center y. The center y part is definitely right. And as I say, because the nose is a little bit off and I can see the beginning of that eye, I think it is about 4. So that seems about right. We'll know for sure soon. Okay, let's see. Let's finish up. This is the stub. We're going to use the template from cat. Let's go get that template. We'll rename this to render. And let's see, we need to render the cat image in an appropriate place on MTS. Cat is itself the x coordinate. So looking at the signature, the purpose, and the example, what I can see is that this is placeImage cat image. C is itself the x coordinate, CTRY, and MTS. I'll run that. Both my tests are passing. And now what I'd like to do is actually run the world program. So going back to main, I could call main, and the initial world state is whatever cat I give it, whatever x coordinate I give it. So it probably makes sense to maybe call it with 0 to start. So I run the program, and then I get this interaction window down here, and I go main of 0, and there's my cat walking across the screen. And now that I have a clear sense in my mind of what's a good default way to start this program, what I'm going to do is go back to the main function and say start the world with main of 0, just as a way of telling people what's a good way to start it. I actually could have put in that start the world with main 0 at the beginning, because as soon as we knew what the cat data definition was, we knew that 0 would be a good default value. I just waited to the end here. So there we go. We've got a complete running world program. One of the things I hope you saw here is that by working systematically at any moment in time, our work was very focused. Even though we did a lot, at every moment in time, we were only doing one thing. That's what working systematically did for us. So when we were working on the domain analysis, even then there were parts of it. We worked on the constant information. Then we did the changing information. Then we did the Big Bang options, and that gave us the domain analysis. As we started building the program, first we did the constants. Then we did the data definition for changing information. Then we set up the main function and the wish list for our Big Bang option handlers. And then we work that wish list one function at a time. This is really important as programs get big. And remember, programs get big. Cars have millions of lines of code in them. The big benefit of having a systematic process is it lets you work on one thing at a time and know that it's all going to work out. Because in this case, when we were done and we said main of 0, bang, we got a running world program. And also, let me repeat a point I made earlier about templates. Because we have a process, some parts of the work we do don't really necessarily end up as specific subparts of the final program. So the domain analysis itself isn't in the program. It's something we wrote on a piece of paper. But it was part of the process that got us there. That's just like the template. The template kind of disappears into the final function definition. But the template is part of the process that gets us there. People who design methods, so that's a kind of meta design, that's one of the things they work on, is how can there be elements of the design that get you there even though they disappear in the final artifact. We'll talk more about that as we go along.